On this channel, we provide useful programming information with practical code examples. This time, we'll cover TypeScript and web storage. We explained TypeScript and web storage, including practical examples. Enabling subtitles will make the code descriptions easier to understand. The browser's web storage is a key-value storage for strings. It's lightweight with a synchronous API, but be mindful that it can store strings only, and you must handle exceptions such as exceeding the storage quota. When combined with TypeScript, you can add type safety, safe serialization, deserialization, centralized key management, and expiration and versioning, resulting in a production-ready design. Local storage is persistent storage that remains after closing the browser, while session storage is per tab window session storage that is cleared when the tab is closed. Both store values as key value pairs, strings. This code is a sample for saving and retrieving strings. Because web storage can store only strings, objects must be converted to JSON to be stored. If you actually run the code, you must do it within the HTML file. In this video, we only check that no compilation errors occur. To store and restore objects in web storage, use JSON, stringify, JSON, parse. This code is a minimal working example. In real applications, you must also account for exceptions such as parse failures and running out of storage quota. Here, we provide a wrapper to make reads and writes safe and handle JSON, parse failures and set item exceptions. You can reuse this utility across the app. Wrap further when you want to add try, catch. Since web storage itself has no TTL, manage it by adding an expires at to the value. TTL is effective for cache and autosave drafts, and can reduce inconsistencies. Standardizing keys as prefix plus version plus name reduces collisions and simplifies migrations. Including a namespace in the key makes it easier to switch versions or perform cleanup later. Consider that a quota exceeded error may occur when running setItem, and design a fallback strategy for when saving data fails. For example, when you exceed storage capacity, you can delete old data or fall back to session storage or an in-memory cache to maintain overall app stability. Depending on the fallback destination, data persistence may not be guaranteed. Therefore, choose an appropriate storage destination according to your use case. For example, in private browsing mode or under storage limits, you can maintain functionality by temporarily using memory or session storage. Using Window Add Event Listener Storage, you can detect storage changes that occurred in other tabs. However, this event does not fire within the same tab. Therefore, for change notifications within the same tab, publish your own events using Custom Event. With this code, you can synchronize storage changes across both other tabs and the current tab. Define a key-to-type map in TypeScript to prevent mistakes during saving and retrieval. To correctly restore objects such as date and map, leverage the replacer and reviver of JSON, Stringify. Using this method, date objects are correctly restored as date. Similarly, map and set can also be marked and restored. If you might change the storage format in the future, include a version in the payload and prepare migrations. By stacking small migrations, you can maintain backward compatibility. In environments without window, directly referencing local storage will crash, so use environment guards. For code that must support SSR, always remember to check type of window. Let's look at an example implementation of a generic class that integrates the elements we've covered so far, including namespaces, type safety, expiration, TTL, and exception handling. In actual products, consider adding tests, logging, LRU-based deletion of old data, encryption, and more. This code shows the configuration and type definitions for building a type-safe, feature-rich key value storage. This code is the core of the typed storage class that provides type-safe key value storage. It manages the allowed keys and their types based on the registry and generates prefixed storage keys. Furthermore, it uses local storage and an in-memory fallback, and lets you set an event name for same tab change notifications. The get method retrieves the value for the specified key in a type-safe way and can optionally handle values with a TTL expiration. The set method saves a value under the specified key and returns a boolean indicating whether it succeeded. The set with TTL method saves a value with a TTL expiration. The remove method deletes the value for the specified key from both storage and the fallback. The clear method deletes all data stored in both storage and the fallback. This code is an example using typed storage, which saves and retrieves values such as theme and draft in a type-safe key value store, and also supports TTL and a fallback. It configures same tab notifications and an in-memory fallback to perform storage operations safely. The typed storage class is a practical starting point. Implement LRU strategies, encryption, compression, and fallbacks to IndexedDB as needed. When using web storage with TypeScript, always keep in mind 4 points: type safety, exception resilience, security, and synchronization, multiple tabs, for a robust design. The wrappers and utilities we've seen so far are examples of that. You can also migrate to other browser storage such as IndexedDB as needed. The source code for this video can be downloaded from the official website. If you like, please visit the URL in the description to aid your learning. If you found this video helpful, I would appreciate your support by subscribing to the channel.